Hello, everyone. Thank you so much for joining us. Today also the video is recording. This is the session 43 in Material Science and Engineering Club. Thank you for participating in this session too. We are gathering here to discuss about new subjects in material science and engineering. And we are here to have a critical thinking about specific subjects. We invite all specialists and professors or engineers all around the world to talk about new subjects and share our opinion and knowledge together. So for this session, we are honored to have Dr. Reza Javaherdashti from Netherlands. He is with us. We can start the session with his introduction, and then we will have his presentations for the rest of the this session. We are inviting you to participate during his presentation. Every 5 minutes, 10 minutes, we can stop. And all of you can raise your hand or write your opinion, your question in chat. But we prefer to hear your voice. Please raise your hand. We will transfer the microphone to you. And you can talk about your opinion or share new idea with us. So I will stop talking. I want to introduce you Dr. Reza Javaherdashti, and after his introduction, he can continue his presentation. Hello, Dr. Javaherdashti. Please go ahead.
Hello. Good morning to you all. Thank you very much for attending this session with me on a Sunday morning, and I hope that everyone will enjoy this presentation on microbial corrosion. During the presentation, I will have a short section that in that section, I will introduce myself quite shortly. We will go through the main part of the presentation, and after that, I'm ready to get your questions. Although, as you mentioned, you're also welcome to ask your questions during the presentation. But if your questions need to be explained in full details, we can always do that at the end of presentation. All right. If everybody agrees, we can continue, or if you want me to wait a little longer, that's fine. Just let me know.
Thank you so much, Dr. Reza. I don't see any raised hand, and there is no point in the chat, so you can start, you can share your file, and we can hear you. Thank you so much.
All right, thank you. Thank you. I hope that everybody can see my screen now.
Yes, we have it.
Yeah. First, I would like to thank you and your colleagues for orchestrating this webinar on microbial corrosion. And I'm quite glad that this opportunity has been given to me to talk about a very important issue, which is microbial corrosion. And why it is important, because as I will continue my presentation, you will see that there at the moment it is one of the major issues in many countries, particularly in Canada, and it is also some sort of heartbreaking to see that there is almost no contribution from researchers or engineers in Canada regarding microbial corrosion. Although there could be a few, but it is not as extensive as it is right now in China, for example, or even in the US, or even in some Persian Gulf rim countries. And it is despite the fact that in Canada, you guys have gas pipelines, you have power plants, etc., etc. And therefore, it is a very important issue to actually talk about important issue of microbial corrosion. Before everything, I want to start with this table that actually defines what we mean by risk and likelihood of a danger. Risk is a function of both likelihood and consequences. It means that no matter how unlikely or even rare the likelihood of, say, microbial corrosion be, as long as the consequences associated with it can be categorized as major or critical, the risk is high. Therefore, we must not mix up between risk and likelihood. Why I put this slide at the beginning of my presentation, and we will get back to this slide towards end of my presentation too, it is because many industry managers, professionals, they do mix up likelihood of a danger like microbial corrosion with its risk. They say that, yeah, okay, so far we haven't had any major problem, so we don't need to bother ourselves with MIC. These guys actually think that because the likelihood of MIC in their facilities is unlikely, therefore its risk must be low too. This approach is wrong because of the consequences that it could involve. When we talk about consequences, we mean either damage to the environment or financial loss. Like, for example, if you have microbial corrosion in fire water rings in a refinery or in a power plant, and due to microbial corrosion, you get the ring filled with corrosion scales. This means that in the event of fire, you will not be able to operate the pumps for emergency water efficiently enough. Thus, you will lose. And there is a case that during my presentation, I will share it with you. It happened back in Australia, and back in 2000 and I think 7 or something, something that they could have easily solved by paying just $50,000, they had to pay $1 million to remediate. So one wrong approach is that so far so good, we haven't had any problem. Another wrong approach is that we have taken care of all possible measures. Therefore, it is unlikely to have any case of microbial corrosion. Again, the same fallacy, the same wrong philosophy. Just because the likelihood is low does not necessarily mean that the risk is low. We will get back to this option later. As I said, the general organization of this talk will be in 3 parts. In part 1, we will talk about required information to learn the topic, because without having a sound knowledge about the case of microbial corrosion, what it is not, we may not be able to really understand the root cause behind the cases that we will discuss in part 2. In part 3, we will hopefully have challenging discussions so that we will be in a position to actually get a better idea about microbial corrosion. A quick self-introduction. My background is in metallurgical engineering and material science. I did my PhD and postdoc both in Australia on the subject of microbial corrosion of steels, as well as biodeterioration of reinforced concrete. Then I've been involved in more than 400 corrosion management projects worldwide. I am honored to be approved by both ASME and Society of Petroleum Engineers, SPE, as corrosion lecturer for microbial corrosion. And so far, I have more than 5,000 hours experience globally for several industries for designing and successfully carrying out workshops on electrochemical corrosion, microbial corrosion, and corrosion management. I have authored several books, and at the moment, I am the CEO of MIC Core, which is a boutique consulting company in the Netherlands. These are some examples of my books, authored or co-authored, and they have been published by publishers such as Springer, CRC Press, Elsevier. Two recent books that I have authored and edited are the one on corrosion management, published by Wiley, with the title Corrosion Policy Decision Making. And then there is another book that is called Pathological Mini Atlas of Microbial Corrosion and Deterioration. This is the first ever of its kind, and it has several case histories with good quality pictures and explanations. And in this presentation, I will use some of these cases too. All right, let's start part 1. From an engineering point of view, or better to say, if we look at the consequences of corrosion, annual cost of corrosion to industries worldwide is much more than the annual cost of all natural disasters combined. The costs imposed by fires, tsunamis, hurricanes, floods, etc., etc. The cost of all these natural disasters combined is still less than the annual cost of corrosion to a given country. For example, if we take the Netherlands as an example of a European country with advanced industry, estimated annual cost of corrosion has been around 20 billion euros. And the cost of microbial corrosion, abbreviated as MIC, ranges between 10 to 40% of the cost of corrosion. Why it is such a wide range given for MIC costs? It is because of the reasons that we will discuss shortly. During my life, I have had the honor of meeting 4 types of people when it comes to their attitude against microbial corrosion. The first group are those who totally deny existence of such a thing as MIC. They simply deny that bacteria, or rather, generally speaking, organisms could have any effect on rate and severity of corrosion. Then we have those who accept that there is something called microbial corrosion. However, it is only limited to sulfate-reducing bacteria, or shortly known as SRB. Yet, one level higher are those who believe that yes, there is microbial corrosion, yes, there are sulfur-reducing bacteria contributing to corrosion, but in addition to SRB, we do have other types of bacteria that are also contributing to corrosion. And the highest level of understanding of microbial corrosion is, or better to say, belongs to those who believe that in addition to involving SRB and some of other bacteria and organisms, Clostridia bacteria are also an essential part of any MIC scenario. We will come to this point, and during this presentation, this short presentation, I will just try to present to you what that I normally present within 5 days and 40 hours. So please bear with me if sometimes I have to just jump on some slides and go through fast. But if you think that I have to get back and slow down and concentrate more on a given slide, please just let me know. All right.
Sorry, Dr. Reza, if you have a short pause here, if other participant, they want to participate or ask a question, have a pause here. If anybody wants to add some points, you can raise hand or write it in the chat. During to see any reactions, I have a question, Dr. Reza.
Yes.
You showed one slide about the role of MIC in the costs, and I remember this is sorry, the previous no, I think slide 6 or 7. It's about 10 to 40% of the corrosions. Yes, here. Yeah. I want to know that here, is MIC the main reason of corrosion, or does MIC accelerate the other corrosion mechanism?
That's a very good question. Actually, it can do both. And this is a concept that I have introduced to the literature of corrosion some years ago under the name of series and parallel corrosion geometries. It means that sometimes corrosion reactions can happen in a series geometry, that is, one corrosion reaction accelerates the other, and it goes like that. Or sometimes more than one corrosion reactions happen in parallel form, so that you can have microbial corrosion reactions going on in parallel to others. Just let me give you an example. If you take a pipeline, microbial corrosion can happen inside the pipe, whereas outside the pipe, you could have, for example, atmospheric corrosion, and they are not attached to each other. However, it is quite possible that within the same within the same pipe, you have microbial corrosion that is accelerated by, say, galvanic corrosion between the weld line and the parent material of the pipe. So both scenarios could be operative.
Thank you very much. We have a request or question in the chat, Mr. Ahad.
Yes, please. Yeah, if you don't mind, I would like to ask that instead of putting questions in the chat, like yourself, ask it, so that I can hear the question instead of reading it.
Yes, sure. Because the video is recording, it's better to other audience that they will go to the YouTube. They want to watch again the video. They can hear or know the question also. So here,
Yes.
Mr. Ahad asked, please explain the difference between normal corrosion products and MIC in your slide. Maybe you have it in the future. I don't know.
Yes, I will.
Okay,
I will.
good.
I will.
There is no other points. If you want, you can continue.
Okay. But just a quick touch. When it comes to corrosion products from MIC processes, there are some guide products or guide minerals that we can actually point to, but they are not, just knowing that, for example, you could get iron sulfide in the form of maquinavite is just one part of the puzzle. When you have a case of microbial corrosion, during my 20-odd years of experience in both academia and industry, what I have learned is that you are basically dealing with a crime scene investigation type of approach. You have to pick up all the bits and pieces and put together. Just focusing on peat morphology or mineralogy of corrosion products, etc., will not help you. You have to put together all these bits and pieces together to arrive at the what you call it, at the idea that yes, the type of corrosion I am observing is indeed microbial corrosion and not, for example, weld decay or a straight current corrosion or anything as such. We will have, hopefully, we will have time to discuss these matters in details. All right, so there could be two approaches towards microbial corrosion. One is material-based, another is system-based. What does it mean? It means that if I'm working in industry, I may say that I am just interested in knowing MIC in pipelines or in heat exchangers. I don't care if, for example, it is happening in, I don't know, a desal plant or steel piles of jetties. So you concentrate mainly on the system or on the asset that you have. Yet another approach is material-based. You say that if I know under what conditions a certain material, like for example carbon steel, undergoes microbial corrosion, it doesn't matter in what equipment it has been used, in what industry it has been used, in what country or region it has been used. If I know that carbon steel undergoes microbial corrosion under such and such conditions, it doesn't matter if it is a pipeline, an oil pipeline or gas pipeline in Canada, or a condenser as a part of a water vapor circuit in a power plant in China, or as a tank, a fuel tank in Saudi Arabia. It doesn't matter. working conditions only dictate what constraints could exist, temperature-wise, pressure-wise, fluid velocity-wise, etc., etc. Therefore, our approach must actually contain both material and system approaches. If we are considering microbial corrosion in a, say, in a submersible platform, we need to know on what material we are basically considering MIC, and the same for others. So I will try to use a mixed approach of both material based and system based. A little bit microbiology 101. Life, as we know, can be categorized based on the cellular form into two categories: eukaryotes and prokaryotes. Eukaryotes are cells that have a nucleus, like, for example, human cells, plant cells, animal cells. On the other hand, prokaryotes are cells with no nucleus, such as bacteria and their cousins, archaea. Why I call archaea like cousins of bacteria? Because like left hand and right hand, they are similar to each other, but they are not the same. That's why archaea can withstand some conditions to which bacteria have no resistance, and vice versa. There is also one more thing that here I have written by red colored lines. In one, it says eukaryotes evolved by modification of their own existing genetic material, and prokaryotes can evolve by horizontal gene transfer. What these two sentences mean simply means that human beings produce human beings, or lions produce lions. You cannot expect human beings to have children like lion cubs. Why? Because eukaryotes evolve by their existing genetic material. However, this is not true for bacteria. A bacteria that can reduce sulfate under certain circumstances can act like a iron-reducing bacteria and therefore reduce iron. Therefore, it is not something that when we talk about bacteria, you may have heard that we talk about iron-reducing bacteria, sulfate-reducing bacteria, etc., etc. These are all conventions. They do not exist under real life conditions. Bacteria do whatever they can, even by doing something that has not been defined for them just to survive. That's why bacteria have survived billions of years on this planet. And that's why they have quite amazing capabilities to actually deal with many adverse conditions. The size of bacteria or prokaryotes is in the vicinity of 1 micron. They are smaller than human cells, and they are bigger than viruses. Viruses do not impose corrosion. However, bacteria do impose corrosion. We will talk about it in a minute. There are some factors that can be used to classify bacteria. These factors are known to microbiologists, but I'm not going to discuss it as a microbiologist, but as an engineer and how important they are. Like, for example, when it comes to the shape or morphology of the bacteria. Bacteria could be found in several morphologies, the main important of which is that some of them, they can be found as coccus, like small balls, or like small sausages, bacillus, or like these spirals. The importance of the shape of the bacteria is that if the bacteria you have has a bacillus shape or morphology, it means that you are in trouble. Experience has shown that bacillus bacteria could highly resist adverse external parameters, such as, but not limited to, chemical treatment. Therefore, when you have a case of microbial corrosion, you have to instruct your test house to also provide you with enough information related to the morphology and shape of the bacteria. Another issue is with oxygen requirement. Some bacteria, obviously, they require oxygen, and they are termed as obligate aerobes. This means that, like us, like human beings, they do need oxygen. Then it comes microaerophils. Micro means small, aero means air, and philos means loving. So microaerophils means bacteria that can still deal with growth and activity if the oxygen in the system is not that much. Then it comes to obligate anaerobes. They absolutely need no oxygen. If you have a little bit of oxygen in the system, they will die off. And sulfur-reducing bacteria, SRB, are a good example. Just imagine on the surface of Earth, where oxygen is the main factor that keeps us, when I say us, I mean all organisms alive. Just imagine that oxygen will act like a toxic material to anaerobic bacteria, such as, but not limited, SRB. Then we have facultative anaerobes. It means that depending on availability or lack of oxygen, they can survive. That's why they are called facultative. Then we have capnophils, where they need CO2. And it is interesting to know that in industry, one of the ways by which they think they can preserve pipelines that have corroded and they think they have cleaned it enough is to fill it with CO2, and therefore they think that they have filled the pipe with rather inert gas, such as CO2 or nitrogen, but they don't know that actually if they have capnophils, for example, within the environment inside the pipe, they have actually provided the bacteria with food. Then comes the impact of temperature. Bacteria can be, so far what we have found is that they can be categorized in three large categories. Mesophils, the one in the middle, they can survive and grow within a temperature range that it is called as room temperature. And that range has been mentioned here in both Celsius and Fahrenheit range. Then we have our Abadani friends, thermophils, with their rather famous sunglasses. These thermophils, they prefer high temperatures, above 65 degrees centigrade. And I have seen bacteria that have been active in the vicinity of 120 degrees centigrade. Archaea are thermophils. And then we have psychrophils that can actually be active and growing at very low temperatures. Therefore, just because within your refrigerator you have low temperature does not mean that no bacteria is there. On the contrary, you could have a jungle of psychrophil bacteria inside your refrigerator. There are 6 correct ways to name microbial corrosion. You may say that, okay, but why you have put here 7? Because number 7 is wrong. Back in 1993, when instead of ANPP, there was NACE, they officially named this corrosion process as microbiologically influenced corrosion. And they abbreviated as MIC, or as our Yankee friends call it, MIC. Then we have microbially induced corrosion, again abbreviated as MIC, but this is the term that in rather European countries, the UK, Australia, they prefer to use. Essentially, they have no difference. Then we have microbial corrosion. Another way is biocorrosion, biological corrosion, biofilling. However, calling this corrosion process as bacterial corrosion or bacteria-induced corrosion is wrong, because in addition to bacteria, you could also have the impact of archaea, algae, fungi, and so on. If you are living in the United States and you talk about this corrosion process as biocorrosion, they would think that you are talking about microbial corrosion of body implants. So mind you, in the US, biocorrosion is, especially during these years, is exclusively used to address microbial corrosion of body implants. During this presentation, I will either use MIC or microbial corrosion. Before we start definitions, is there anything our friends want to ask?
Thank you, Dr. Reza. If any participant they want to join us and share their idea or questions, please go ahead. Please raise hand or open your microphone. We can hear you, or write it in the chat. We will read your question or points. Up to now, yes. Please, we have a guest from World Academy. Please.
Hello, Dr. Tabai.
Hello.
Can you hear me?
Hello, Dr. Javadi,
Hello.
please.
Yeah.
Yes, we can
Thank
hear
you. Thank you very much for interesting presentation. Just in your previous slide, I saw that you mentioned this high temperature bacteria, but in the left, you somehow focus up to 50 centigrade. Is it just a kind of schematic to be revised, or there is a reason that you focus just up to 50 centigrade?
No. Actually, as I said, there is with a probability of 95%, you can find thermophile bacteria in around temperatures like 60 degrees centigrade, 65 degrees, but there are odds where they can survive temperatures even above 100 degrees centigrade, such as Tormotegaceae. Tormotegaceae, they can survive temperatures well above 100 degrees centigrade due to toga, due to the sort of coating they have around their body that would make them resistant to heat. So this is to say that thermophiles, they just prefer high temperatures.
Okay, then the bacteria in petroleum engineering, for example, for enhanced oil recovery, belongs to this group mostly, or?
Mostly. If we
Thank
are
you.
talking about the bacteria population within a well, yes, mostly they will be thermophile bacteria.
Thank you. Thank you.
You're welcome. And yeah, okay. There are these four matters here. Microbiologically influenced corrosion, or MIC, is a type of corrosion inhibited, enhanced, or that can initiate, enhance, or even inhibit by the action of bacteria. So not all the time having bacteria around is a sign that corrosion will be enhanced. On the contrary, under certain conditions, actually having bacteria could reduce and decelerate corrosion. This is a very important point. Then almost all engineering materials, including non-metals such as concrete and polymers, are prone to attack by bacteria. Perhaps in future, I will have the honor of meeting you guys again to talk more about biodeterioration of concrete and polymers, but I will not cover these important concepts in this presentation, perhaps in the future. The cost of corrosion in industrialized countries is about 4% of the GNP of the country. GNP is gross national product that actually reflects the average income of a country's citizens. If you look at the background history of cost of corrosion studies back in late 1940s, we now can say that the cost of corrosion floats within a range of 4 to 7% of the GNP of a country. Like, for example, in 2000, a study in China showed. Okay, do you hear me?
Yes, we can hear you, but
Okay.
you had an interruption in your, I think.
Yes, I got that message. That's why I went silent. So, as I was saying, in 2018, if I'm not mistaken, a study showed that the cost of corrosion in China, for example, was around 7% of their GNP. It means that out of each $100 that a Chinese citizen earns, $7 automatically is gone due to corrosion. MIC has been reported to account for 20% of all the damage caused by corrosion. If you remember, previously I said that the cost is between 10 to 40%. This 20% is has a rather interesting story. In many papers and books, this figure, 20%, is quoted and written. And I think I was the only person and the first person who tried to find out where this 20% is coming from. To cut the long story short, I reached to the original author who had put this figure, and I asked him about from where he had brought this 20% figure. And what he simply said in his email to me was that, Reza, it was just a wild guess. So you have such cases that actually puts too much uncertainty to considering the economy associated with MIC costs. And there are basically three reasons for that. The first reason is that, to the best of my knowledge, no government or industry-funded study is there about the real impact of corrosion. From what I know, that apart from the US, no other country has such figures. Even in Canada, I did a research, I couldn't find anything. A few years back, there was a report, official report, published by NACE called Impact. And I guess there was also an Impact Canada published. And as far as I remember, I couldn't find any figures regarding the direct or indirect cost of MIC in Canada. Then many of MIC cases are not even recognized until the near failure status of the system. I have been witness to that several times. I have approached industries in Australia, in the US, in the UK, in the GCC countries, many parts of the world. And I have advised them that under their current working conditions, it is quite possible that they will get corrosion and particularly MIC, and they have not listened. They have said that, no, everyone looks fine, no problem. And then after 1 month or so, they have called on me and they have asked me to make miracles for them by rescuing, by salvaging their asset, which is almost important. Almost far beyond being carried out successfully. The last but not the least reason is stereotyping about MIC, so that it has become an industry joke. The guy has a case of corrosion. He cannot explain why he gets very high corrosion rates, like 36 MPY. And then he says that it must be bacteria. They put all the blame on bacteria, which could possibly be wrong. And I am also witness to that. So if the cause is not MIC, and you assume that it is MIC, and you apply mitigation programs that are not meant to be used for that case, you have wasted money, and then you have not actually mitigated the issue. And next time, when the case is MIC indeed, nobody will listen to you. All right. MIC can be seen in many industries, like chemical industry, marine industry, pulp and paper industry, wood processing industry. Anywhere you have water in liquid form, there could be a possible nominee for microbial corrosion cases. So in a sense, I can say that almost all industries are vulnerable to microbial corrosion. All right, before starting this new topic, which is quite important, is there any questions?
I don't see any question or points in the chat and no raised hand.
Okay.
Please, Dr. Reza, go ahead.
Okay, let's continue then. Bacteria, when they go through colonization, they go through two stages. In stage one, initial attachment of bacteria on the surfaces happen, and it is reversible. So if you are alert enough, you may be able to actually stop it and control the disaster. However, what happens most of the time is that stage one is not recognized, and then it is stage two that happens, that we call as biofilm formation. Maybe you have heard this terminology, biofilm, that later I will explain that it is a wrong terminology for a correct process. What does it mean, biofilm formation? It means that bacteria, they start to produce a material that is called as extracellular polymeric substances, EPS, and therefore by secretion of EPS, they attach themselves to onto the surfaces quite strongly. Stage two, contrary to stage one, is not reversible. And when biofilm formation happens, it means that you are in trouble. Let me give you an example. If initially you have just 3 bacteria, and it takes 15 minutes for them to reproduce or regenerate, within about 4 hours from the initial 3 bacteria, you could end up in more than 190,000 bacteria. This is how rapidly they could actually regenerate. And this is something that you cannot afford. Schematically, biofilm formation can be summarized as these 6 stages. And before I explain, so far, biofilm formation has well been explained for water-containing environments, like, for example, for systems containing seawater, like pipelines under hydrostatic testing, or for fluids that have an entrained water phase with them, like oil or gas. What happens is that in the water, we have bacteria that they can find their food, nutrients from the bulk water. In this state, they are called planktonic bacteria. Planktonic means freely swimming around. Why they are freely swimming around? Because they can find food from the bulk water. But if this food sinks down under its weight and under the effect of gravity on surfaces, bacteria recognizes that food on surfaces is much higher in quantity than food in the bulk phase. How they do that? Possibly by something that we call as quorum sensing. So they sense that there is no more easily accessible food in the bulk water. They have been collected on surfaces. So what they do, they create a conditioning film, a sticky film. All right. Then they start to sink slowly and establish themselves on the conditioning film. Picture number 2. During this process, they start to grow hands and legs, which are in a sense made up of that exopolymer material, EPS. And this, like anchors, help them fix their position on the surface and become almost motionless. They will not be able to swim anymore. In this position, or in this state, they are called as sessile bacteria. When bacteria come to sessile bacteria state or status, this does not simply mean that they have become motionless. This also means that they have gone through a process in which their genetic structure has also been changed. They have come up with higher capabilities for having accelerated accelerated mechanisms for using energy, so they can grow faster, much faster than when they were at planktonic state. All right. When it comes to number 3 and number 4, you see that they have started to grow in size, and by that, as I said, their metabolism will be changing as well. When they come to a certain level of thickness, for example, around 2 angstroms, the oxygen below the bacterial film becomes depleted. It becomes anaerobic. Why? Because by time a diffusion layer is formed by increasing the thickness of the biofilm. A diffusion layer is formed so that oxygen and nutrients or food will be much difficult for them to enter into the body of the biofilm. What does it mean? It means that the bacteria which are located at the bottom of the biofilm, in the surface, in the what you call common surface between bottom of the biofilm and surface of the conditioning film, they will die off because they are not receiving oxygen. If they are aerobic, they are not receiving food, they die. However, their bodies are still there. They are like zombies. They are not alive, but they are there. Now, if there is any change in the hydrodynamics of the fluid, like for example, an engineer somewhere has read or has heard from a self-proclaimed MIC expert that you must always keep water flowing because it is a stagnant water which is more likely to develop biofilms. Then this engineer, this poor engineer, starts to run the pump to provide, kind of force. However, by doing so, without previously cleaning the surfaces, a part of the of the biofilm is taken off because the bacteria, the bugs are dead. They are just sitting there like zombies. And when that happens, as you can see in picture 5, you will have areas where you have biofilms and you don't have biofilms, which is the best places for developing electrochemical cells, such as differential aeration cells, where low partial pressure of oxygen creates anode and high partial pressure of oxygen creates cathode. Picture number 6. And where anode is developed, you will get pitting potential. All right, and this is a schematic conceptual view of biofilm. As you can see, it is quite an open structure. Gases, material could pass through. However, when they have a very high thickness, it may not be easy for these gas and nutrients to actually diffuse into the internal parts of the biofilm. Those black dots you see are actually representing bacteria. What does it mean? It means that when you apply biocides, which are chemicals that kill bacteria, the bugs, the bacteria which are on the roof of the biofilm, they start to die, but at the same time, they start to send signals to their cousins to speed up their metabolism and increase the thickness of the biofilm. And what does it mean? It means that by doing so, by increasing the thickness, the diffusion path will increase. Therefore, for the biocide or any toxic chemicals to go through the biofilm and become effective, it will take much longer times, and therefore the biocide may not be effective on the biofilm. Therefore, what you see as a biofilm, it is not like a coating. It is a live structure. It can repair itself. It can be always full of surprises, like increasing metabolism to increase the thickness. The bacteria here can actually go on fasting with very low amount of food. They can survive. That's why I said that when you come to irreversible stage 2, you are in trouble. When you have biofilm, you have a lot of problems. To summarize, you have these 5 steps. In number 1, you have bare metal surface. In number 2, biofilm starts to be formed. Number 3, biofilm starts to grow in thickness. Then a part of it could be removed. Number 4, but the rest of the biofilm that remains could start to increase its metabolism with very low level of food, and regrowth happens in number 5. And therefore, you see that anode, or better to say pitting at anode, can be formed here, and how this biofilm could look like. Is there any questions?
Thank you, Dr. Reza. If there is any question, any idea, please open your microphone. We can transfer to you. Yes, I think Dr. Javaherdashti, please go ahead.
Thank you for interesting presentation. My question is, do you see any importance of quorum sensing phenomena also for this bacterial corrosion? Is there any studies in this regard?
I couldn't follow. Could you please
The quorum sensing is generally how bacteria has a kind of, let's say, signaling.
Yes, that's what I mentioned. Quorum sensing. Yes.
Yeah, exactly.
Yeah.
And because what we do, we have a group on bio interface in
Yes.
World Academies, because my main area is colloid and surface phenomena.
Okay.
And for example, for us is important that how the surface activity of bacteria play a role
Yes.
for film formation, and what can be the role of surface activity of the bacteria in quorum sensing phenomena.
Yes. It is indeed important because it is via such phenomenon, like as you mentioned, quorum sensing, that bacteria would communicate with each other and would make biofilm like a fortress into which penetration will be quite difficult.
Okay, and have you seen any available research work, papers, or theses on how we can quantify quorum sensing and bacterial film formation, considering quantitative analysis of dynamic surface properties? Because this is something that we try to develop a project on that, that how we can make a better linkage and better insight in this regard. Are you aware of any research work that how we can make a link between the quantitative dynamic surface properties of bacteria and related products like biosurfactants with these phenomena?
Yeah, I have seen many papers on mathematical modeling of biofilms, and as a matter of fact, at the moment, with a group of colleagues from around the world, we are authoring a book about how to model corrosion and microbial corrosion. But for the particular case that you just mentioned, at the moment, I can't remember anything. There might be, but at the moment, I can't remember any. I mean, it doesn't ring a bell.
Okay, thank you. Maybe when you have time,
Yes, sure.
with the support of Dr. Tabai, or maybe our mentor here, Ms. Jafari, you can attend the group of bio interface on World Academies. Maybe later we can have joint discussion session. Thank you.
Definitely. Thank you.
Thank you, Dr. Reza. We have another participant who wants, I think, Professor Reza. Please go ahead.
Please, yes.
Yeah, one question is, you consider this surface is plan.
Sorry?
While in the industrial the surface you mentioned, you didn't talk about the state of the surface, the rough.
Okay. Actually, yeah.
The effect of the roughness.
I see.
Surface on this corrosion.
I see.
Thank you very much for your presentation.
Thank you. I got your point. Actually, rough surfaces are highly likely to contribute to initiation of microbial corrosion. If it is rough, it means that, simply put, it means that there are more rooms for bacteria to harbor in. However, having said that, if you look at the simple stages here and pictures here, you see that you have conditioning film. This means that no matter how rough or highly finished your surface is, it is also possible that because bacteria are basically sitting on the conditioning film, which is an interface between external environment and the metal itself. So for them to actually sit on surfaces, there is, practically speaking, there is no obstacle. They can sit on surface of a stainless steel as simple as the way they sit on, say, concrete surface. You know what I mean? But roughness has a contribution. If the surface is rough, for example, you have done welding and you have not done post-welding treatment by removing the rough surfaces. This will increase the likelihood of biofilm formation. Okay, isn't there any question? Any other questions?
Thank you all participants.
Okay.
There is no question in the chat and no raise hand. Please let's continue.
So if there is no question, now it is my turn to ask a question. In this slide, and actually in one of previous slides, but let's concentrate on this slide. I have made a mistake deliberately. What is the mistake I made deliberately in this slide? You have 1 minute to think and then answer me. What is the mistake I deliberately made in this slide?
At least in one of the slides, we see that the interface or substrate is two-part. I don't know why this is different with the others.
Well, that is supposed to show pitting. It is my fault to, I have always been bad at drawing, but it is not the mistake. Let's compare this slide with this one. Where do you see the anode? Under the biofilm, right?
Oh, yeah.
You see pitting and anode is happening under the biofilm. Why? Because I mentioned that a differential aeration cell could be formed where spots with lower oxygen partial pressure will become the anode, and spots with higher oxygen partial pressure will become the cathode, right? So here, as you see, the anode is under the biofilm, but here the anode is next to the biofilm. It is outside the biofilm, number 6.
Mm-hmm.
All right. So the correct place of the pitting must have been to the right of the biofilm structure, and therefore pitting must have been drawn under the biofilm, not beyond it. All right, having said that,